Okay. Hello, everyone. So, reminder: I guess proposals are due today, and then I'm going to release PSET 2 shortly, which will be due not next week, but I think the week after next week. Um, okay, good. So we're going to continue with sketching for linear algebra, and we talked already about kind of two approaches to analyzing sketching for least squares. Both of them were sketch and solve. So the algorithm actually didn't change. The only thing that changed was the analysis. So one of the analyses we said, look, if pi is a subspace embedding, and that's the only thing we condition on, then we get something good for sketch and solve. The other thing was we said, okay, let's do the Charlotte approach. Instead of conditioning on it being an epsilon subspace embedding, we'll only condition on it being like a 1/4 subspace embedding, but also that it satisfies the approximate matrix multiplication property for a particular matrix product. If you remember, I think that matrix product looks something like uh, U transpose W, where U was an orthonormal basis for the column space of X, and W was kind of the optimal residual of like U of basically X times beta LS minus Y. So U transpose W should be zero, but somewhere in our analysis, we ended up with something that looked like pi U transpose pi W. So we wanted to argue that that's close to U transpose W, which is zero, and we did that by using the approximate matrix multiplication property, viewing W as a vector, but we viewed it as a matrix with one column. Okay, so that let us get away with fewer rows in our sketch because we didn't need a subspace embedding with as good error. Okay. So today I want to talk about yet a third approach for using sketching to solve least squares. And this is basically using sketching to find a good preconditioner and then feeding that into something like gradient descent or like some iterative solver for least squares. And I put the references for that. And then we're going to talk about how to use sketching for low rank approximation. And just a little big sneak preview, we're going to see that actually this turns out to be pretty much almost. I mean, as we analyze it, we're going to see it pretty much reuses exactly the same kinds of things we talked about for regression. Okay, so let's do these in order. Okay, so I already pre-wrote a little bit. I don't, this is not a course on optimization, so you could say more about gradient descent in general, but all you have to know for today's lecture is, the setup is you want to minimize f of x. F is some function you're given. And you start off with some initial guess for x, for the optimal x star, call that x0, and then you iteratively refine it by moving in the direction of the negative gradient. That a should be an x. I'm sorry. Right. So given that you're currently at some point xt, to get to xt plus 1, you just move a little bit in the negative direction. Think of gamma as being some small number. You move a little bit in the negative direction of the gradient at the current point. And there are general analyses of gradient descent that say, if you know something about, the Lipschitzness, for example, of the gradient of f, or if you have some understanding of derivatives of f, you can prove convergence bounds on kind of how quickly your error decays as you iterate this process. So we're not going to do that today. We're going to focus on the general case. We're just going to focus on the very specific case of least squares. For us, we're trying to minimize x beta minus y L2 norm squared. So I'll just call that f of beta, right? And beta star, which is beta ls, is the minimizer of this. And the way we're going to do it is we're going to pick some initial beta 0 somehow. Actually, this somehow, we're going to get back to that in a second. When we use sketching, there's going to be a very kind of natural way to choose the initial beta 0. And then if you calculate gradients and see, here I put gamma being 1 actually. The direction you want to move in is this direction that I wrote, x transpose y minus x beta t. Okay. So I want to analyze convergence of this. And as you're going to see, something that is going to pop out in the convergence analysis is going to say, look, if x has very good condition number, meaning say like all of its all of its singular values, not just the top singular value, not just the operator norm, but all the singular values are like close to each other. So like the ratio between the largest and the smallest singular value is small, we'll get fast convergence. And then we'll see that, well, okay, so X in general is just some input matrix. X might not have this property that the condition number is small, that all the singular values are close together. And what we'll see is that we can basically force X to have this condition by doing some pre-processing with sketching. Okay. So for now, let me pretend like X actually had this condition. And let's try to analyze this and see what comes out. Okay. So let's proceed. Change. So let's do analysis. Let's do analysis on the right hand side. Okay. So I'd like to understand, let's say, X beta T minus Y L2 norm squared. And I'm going to write this as, I'm just going to add and subtract basically the optimal solution. So this is equal to X beta T minus X beta star. Remember, beta star is actually beta LS. It's just the optimal solution of the least squares problem. Plus X beta star minus Y L2 norm squared. And this is a trick that we've already seen before. These two vectors, this vector and this vector, are orthogonal to each other, right? Because the first vector there is definitely in the column space of X. And the second vector is orthogonal to the column space of X again, because the optimal beta star is the thing that kills the part of Y, which is in the column space of X, right? So X beta star minus Y is basically Y perp. It's the part of Y it's the projection of Y onto the orthogonal space. So these two things are orthogonal. So I can write that as X beta star minus Y L2 norm squared plus X beta T minus X beta star. And again, this is opt, right? That's the best you can do. Okay, so now I want to analyze this thing. So now I'm going to use, let me call this actually, let's say this is actually xt plus 1, this is xt plus 1. So now I'm just going to write down what is beta t plus 1. I'm just going to write down the update rule, which is over here. So this is equal to opt plus x times beta t, okay, plus x transpose y minus x beta t, okay, minus x star, minus beta star. Okay. So I just expanded what beta t plus 1 is in terms of our update rule. And this thing is, there's the opt that's always there. Plus, and then let's just expand this out, x beta t plus xx transpose y minus xx transpose x beta t minus x beta star. Okay. Now I claim that this part right here, okay, is, what is that? It's basically, it's the projection of y onto the column space of, no, sorry, that's not what I want to say. So I just want to say one thing about this, which is the following. I want to say that this is equal actually to xx transpose x beta star. Okay. Now, sorry. Okay. I should figure out how to. There should be a way there was a way again to ignore calls, right? Which was the sleepy sign, I think, right? Okay, good.
Or no, that's just do not disturb. You have to go into your notification settings and turn it off that way.
Oh, really? Okay. Yeah. Let's just hope that isn't coming back then. Notifications. Okay, I'll figure it out another time. So what does the sleepy thing do again?
The sleepy thing is do not disturb. So if your iPad is locked, then it won't like ding or vibrate. Yeah.
Okay, I see. Very good. Anyway, I claim that these two things are equal. Why is that? Because x beta. So remember, I can decompose y as y perp plus y parallel, right? Where y parallel is the part that's in the column space of x, and y perp is the part that's orthogonal. So the point is, like, if you look at x transpose y, that's equal to x transpose y perp plus x transpose y parallel. X transpose y perp is 0, right? Because again, that's x transpose is like basically taking the columns and dot producting them with y, but if y is orthogonal to the column space, then that's 0. So x transpose y perp is 0. The only thing that survives there is x transpose y parallel. Meanwhile, what is x beta star? X beta star is y parallel, right? Right? The optimal beta star is the one such that x beta star is the part of y in the column space of x. So does that make sense? So these two things are actually equal. Right. X beta star and y have the same exact dot products. X beta star is not equal to y. X beta star is equal to the projection of y onto the column space of x. Therefore, dot products with the columns of x are the same for both. So then I can rewrite this thing as opt plus, okay. Let me write it like this. X minus XX transpose X, looks like a mouthful, beta T minus beta star. Okay. And now here's what I want to say. Let's focus our attention on just this part. Okay. And let's write that. Let's write up here that let's just write the SVD of X. So let's just say that X actually is equal to some U sigma V transpose. This is just for the analysis, right? We don't actually need to compute this SVD in the algorithm. The algorithm is just least squares. This is just for the analysis. Okay, so now let's try to understand what's going on here. So we have U sigma V transpose minus U sigma V transpose V sigma U transpose U sigma V transpose times that thing. Okay. V transpose V goes away, U transpose U goes away. This is just U sigma cubed V transpose. So this is equal to, we want to look at again, this, all of this is the norm, right? So this is the square norm of this. All of these are square norms. Okay, so this is now equal to U times, let's write it as 1 minus or let's actually write this. Yeah, 1 minus sigma squared sigma V transpose, and then this beta T minus beta star. Right, you agree with that? If you just expand this out, this is U sigma V transpose minus U sigma cubed V transpose, which is exactly what we said above it should be. Okay. And again, this is equal to dropping the U. Right, because again, since U has orthonormal columns, UX is the same norm of X for any X. And then I can just say, look, the norm of a matrix A times X is at most the operator norm of A times the norm of X. So this is at most the operator norm of identity minus sigma squared times the norm of sigma V transpose times that beta T minus beta star. And again, putting in a u or removing a u doesn't change the norm of anything. So let's put u back. That doesn't change the norm of anything. And then this is just equal to x again. Okay. And the point is now, if all the singular values, if x is very well conditioned, and let's say all the singular values of x are very close to 1, they're all between, let's say, 3/2 and 1/2, or or between 0.9, they're all between 0.9 and 1.1, then identity minus sigma squared, I mean, that's just a diagonal matrix with 1 minus the square of all the singular values in the diagonal. All those singular values we just said are very close to 1. So this thing is very small, right? This thing I can say is at most, a quarter or something, right? Does that make sense? If all the singular values of a are sufficiently close to 1, then I can make sufficient. Then basically this operator norm, this is a diagonal matrix where all the diagonal entries are very close to 0. So in particular, they're all at most a quarter or something. Okay. So now
sorry. I forgot. Why are all the singular values close to 1?
No, I'm saying if we were in such a situation.
Oh, I see.
If x were in such a situation, then we'd be happy. Okay. So now if you look at what we basically have shown, we've shown. Now let me highlight 2 parts of our analyses. I want to look at this part. You see what I've highlighted in the box up above, compared with this part at the end. What I've shown is that x beta t plus 1 minus x beta star L2 norm squared is at most a quarter times x beta t minus x beta star L2 norm squared. So kind of every iteration, this thing is kind of decaying exponentially. Right? When we go from t to t plus 1, it drops by a factor of a quarter, which means that if we go kind of log 1 over epsilon iterations, we're going to drive this distance down by a factor of epsilon. Does that make sense? Okay. Now I want to talk about, going back to your question, how do we know that all the singular values are close to 1? We don't. And that's what we're going to fix using sketching. Before we fix that, I want to say one thing. So basically I want to say that therefore this is at most say, let's say, 4 to the minus t times x beta 0 minus x beta star. Okay. So again, if you run this log 1 over epsilon steps, that 4 to the minus t will basically be epsilon. Okay, so now I want to address a couple things. One is, how are we going to pick beta 0? I said somehow. Okay. The way I'm going to pick beta 0, I mean, you don't have to do this, but here's something you could do. You could just basically pick beta 0 such that x beta 0 minus y L2 norm squared is at most 1.1 times opt. How do you do that? We already know how to do that. Use sketch and solve, right? Use sketch and solve with epsilon being a tenth, right? One of the downsides of sketch and solve is that your complexities, your runtimes have this dependence on 1 over epsilon squared, because you need, or even, if you do the Charlotte approach with AMM, 1 over epsilon, but whatever. Either way, your dependence on epsilon in sketch and solve is going to be poly 1 over epsilon. So if you want really, really good error, you want like machine precision, then, epsilon is going to be tiny. You don't want runtimes that depend on 1 over epsilon. That's terrible. But here, what I'm going to say is, okay, just set epsilon to be some constant, like a tenth. Okay. So this you can do with sketch and solve, where now, your epsilon is a tenth, or it doesn't even have to be a tenth. It could even be, a third, a quarter, something. It doesn't really have to be that small at all. You basically just want to make sure that this thing is at most O of opt, in fact. even that would be, I think, enough. So that you can do with sketch and solve without paying too much in terms of your error parameter. And then now you could bound this thing down here. In the bottom right, I'm circling it in orange. Now you have that x beta 0 minus x beta star L2 norm. Well, now you can just use triangle inequality. This is at most x beta 0 minus y plus x beta star minus y. So I've just added and subtracted y, and then I did triangle inequality. And this is at most, 1.1 opt plus opt. So in other words, this is like at most 2.1 opt. Well, I guess I defined opt to be the square. So this is like O of, I guess, O of root opt, let's say. Which means that if you square it, that's almost O of opt. It's almost 2.1 opt, right? Okay. So now that's great. You're really getting epsilon times opt, right? So epsilon times opt error in log 1 over epsilon iterations. So that's something, if I really want very high precision, that's something that I think makes me happy. I like seeing log 1 over epsilon in my runtimes as opposed to poly 1 over epsilon. Now, okay, now the only thing that's left is you say, well, Jelani, back to the original question, why do I know that x has singular values close to 1? Well, the answer is that it doesn't. But now here's what I do. I compute a subspace embedding. Okay. And I look at say pi x. And pi x is equal to some u prime. I compute the SVD of pi x. But again, and pi is like, let's say, a 1/3 subspace embedding. So again, it's not an epsilon subspace embedding, even though I want epsilon error. It's a constant quality subspace embedding. So it only needs to have d rows, O of d rows. Or if I'm using a count sketch, O of d squared rows. There's no dependence on epsilon here. Okay. And then I compute the SVD. That only takes me poly d time because this is a d by d matrix or d squared by d. And that's equal to u prime sigma prime v prime transpose. And now what I do is I define R, a matrix R, to be v prime sigma prime inverse. Okay. And now what can you tell me about the matrix XR? Okay. So, well, we know that for all x, the norm of x is roughly equal to, it's equal to the norm of, let me call it x. Let me call it z. For all vector z, if you look at the norm of z, it's equal to the norm of pi x rz. Why is this true? Right? It's true because pi xr has, yeah, go ahead.
Oh, yeah, I was going to say pi xr looks like it's just u prime.
Yeah, which has, exactly, pi xr has orthonormal columns, so it preserves the norm of any, vector. But then now I use the fact that pi is a subspace embedding of constant quality, right? So that means that the norm of z is equal to the norm of this, but that's approximately equal to up to 1 plus or minus a third, up to like, 1 plus or minus a third, the norm of xrz. Right? Because pi is a subspace embedding. Pi x times a vector has roughly the same norm as x times that vector for any vector. In particular, the vector here is r times z. So now what we see is that xrz has approximately the same norm as z for all z. That's exactly the statement that all the singular values of xr are close to 1. Meanwhile, xr has the same exact column space as x. So solving the regression problem over x is equivalent to solving the regression problem over xr. Right? Like what, the optima of the two optimization problems are exactly the same. Okay? So everything that I just said, just run it for xr. Do the gradient descent steps with xr instead of x. And then everything works out. And also the nice thing is, like what's the runtime of this? Basically, you need to apply R. So in every iteration, you need to apply right here. Right, you need to apply X to stuff, and you need to apply X transpose to stuff. Now X is actually XR, but R is a smaller matrix, so you can apply R quickly. And X, if you had something, if you were in a good situation like your original X was sparse, great, you're still applying X each iteration, and X is sparse, so you can multiply by X quickly. So you can basically do each iteration in time that's proportional to the sparsity of X plus some poly D term to apply R. Okay. So overall, your runtime becomes something like, sparsity of X times log 1 over epsilon, because log 1 over epsilon is the number of iterations, plus some poly D times log 1 over epsilon. And that the poly D is there because there's a poly D cost up front to compute R, to compute the SVD. And then there's another poly D per iteration. It's like something like D squared to apply R. Okay. So any questions about anything on this slide or on this board before we talk about low rank approximation? Okay, so let's move into low rank approximation. Okay, so what is this problem? So given as input is a matrix A, which again, I'll think of as n by d. But here, it's for the speed up we got for regression, we assumed that the matrix was lopsided so that n was something much bigger than d. Here, it's not going to matter so much, actually. You can use sketching for faster low rank approximation, even for square matrices. And we want to approximately compute, actually, the best rank K approximation to A under some norm. And we decide ahead of time what norm we're interested in doing this in, and also K is a parameter that's given up front. There's a theorem that is like the Eckhart-Young theorem. That the minimizer, the argmin over all B of rank K of say A minus B is equal to AK, which is equal to UK sigma K VK transpose. I'll say what that means in a second. For any rotationally invariant norm. For example, Frobenius norm or L2 to L2 operator norm, the operator norm that we usually talk about. Okay. And what is UK? What are UK sigma K and VK? Remember, we can write the SVD. A is equal to U sigma V transpose, where kind of U is this matrix, sigma is some matrix like this, and then V is some other matrix. So this is sigma, and then V. Right, just maybe be consistent. So there's some U here, and then V is also some other matrix, which is so sigma. What are the dimensions of sigma? As I've been talking about it before, sigma is like R by R, where R is the rank. And then let's say A is N by D. So then this would be N by the rank, and this would be D by the rank. And this is V. Okay. So what is UK sigma K? And again, I know that this is like this thing here. So I guess it's what you might imagine. So UK means I just basically take the first K columns here. And then sigma K means, again, I only take the top K singular value. So again, I also have sigma 1 is greater than equal to sigma 2 is greater than equal to da da da. So they're like sorted in descending order. So I only take the top K singular values, that's sigma K. And similarly here, I only take the first K. Okay. So, by the way, maybe another way to write the SVD to think about is that right? So, yeah, I think you can also write that's the same thing as basically the sum over I from 1 to R of sigma I UI VI transpose. Maybe those are the rows. I have to think about that. I think that's right. Yeah, I think that's right. So actually, I guess I should keep them consistent. These should be superscripts. Right. So this is equivalent. This is the SVD, where the UI are orthonormal and the VI are orthonormal. These are the columns of U and V respectively. And Eckhart Young says that the best rank K approximation is that you only sum the first K of them. Okay.
This is the best K, or the best according to the Frobenius norm.
So Frobenius norm, L2 operator norm, basically any norm that's invariant to rotations. Yeah. Okay, so that already gives, there are algorithms that compute the SVD. If A is N by D, they take time something like N times D squared. I think it's more like, I don't think you compute it exactly. You compute it up to precision epsilon, and the runtime something like N times D squared times log 1 over epsilon or something like that. But the point is, it's like N times D squared, where if N and D are big, that's a lot. And you can ask the question of whether you can go faster. Okay. So as we're going to see, so faster using sketching, we're not, we're going to, rather than compute the full SVD and truncate, what we'll do instead is we'll compute some other approximate version and show that it does okay. So we'll compute a tilde k, I'll call it, which is not the actual optimal thing, but it's equal to the projection onto a pi transpose. So, okay, so I'll say what this means in a second. Okay, this is second. The projection, the best rank k approximation of A in the column space of A pi transpose. Okay, does that make sense? Okay. So, first of all, okay, so one question is like, why does this, what does pi need to satisfy for this to work well? Okay, so we have to analyze that and show why that suffices. And the second thing is like, why is this even better? Like, why is this even faster than computing the full SVD? So here's what we can do. So speed, first let's address the speed because I think that's easier to deal with. So if I want to do this exactly, if I want to compute AK tilde exactly, what I can do is, look, I can first do the following thing. I can say that A pi transpose is equal to some U prime sigma prime V prime transpose. And then what I like to do is I'd like to look at the projection of A to the column space of A pi transpose and take the best rank K approximation. So what I want is the projection of A onto the column space. That's U prime transpose A. And then I'm going to use this bracket K notation to mean I want the best rank K approximation to that thing. Okay. Okay. And what is this? Remember, we already know that to get the best rank K approximation to some matrix, you compute its SVD, and then you compute its SVD, and then you truncate singular vectors and singular values, right? So we already know that, if you write the SVD of U prime transpose A, we already know what the first matrix in the SVD is. It's going to be U prime, right? So I can write this as basically U prime times U prime transpose AK. Okay. Those two things are equal. And I can compute. Let's keep track of dimensions of all these things. So A is an n by d matrix, and then pi is mapping down to some dimension m. Okay. Which means that the rank of U prime, the rank of A pi transpose is at most m, which means that this sigma prime here has dimension at most m. And then this is m, and this is m. Okay, which means that this U prime transpose now, the dimension here is at most m, and then this is n. Okay, and then this is d here. So I can compute in time O of m and d. And then now I need to take the best rank K approximation of this matrix. And for that, I need to compute, one way to do it is to compute the SVD of U prime transpose A. So I can compute the SVD of U prime transpose A in time O of dm squared. Okay. So and then I I'm not gonna multiply everything out at the end. I'm just gonna output like the decomposition as my output. So then I'm done. Basically, I can write so I can write down some kind of decomposition as like this is equal to U prime times a product of some three matrices. So let's call it U double prime times some sigma double prime times some V double prime transpose. And like I'll just output this as my answer. I'll just say that this is my approximate rank K. This is my approximate solution to the best rank K approximation of A. Okay, this decomposition. And I've done it in time MND plus DM squared. And as we're going to see, M is going to be something that's going to be like sort of like K. So the bottleneck basically is this part, where if you compare it to computing a full SVD would have taken time n times d squared. Instead, we're doing something like nd times m, where m is something like k, or k over, it's going to be more like k over epsilon. So we've replaced 1d with a k over epsilon. In fact, it's possible, maybe I'll add it to the lecture notes. I'm not going to do it now in front of you. It's possible to do a little bit even better, where you can replace both d's by k's. So instead of getting an n times d times k, you get something that's more like n times k squared. Okay. And the trick there is to say, look, let me not compute, because if you think about it, like let me not compute this. Maybe I'll write the following thing down. So what I want, trick to go faster. What I really want is to compute the argmin over, let me not call it, argmin over, let's say, matrices X of where the rank of X is at most K of U prime X minus A for Frobenius norm squared. And you can prove that, you can prove that if I solve this without the rank constraint, then I can just take a low rank approximation at the end and still do well. So it can prove that if, like, let's say X star is the opt without rank constraint, you can just return X star, take the best rank K approximation of that. So instead we can say, look, we just want actually the argmin of U prime X minus A for Frobenius norm squared. Okay. And, what we did above is basically trying to solve this kind of minimization problem exactly to find the best thing in the column space of U prime. But I claim that, you shouldn't want, if you want to go faster, don't solve this thing exactly. Observe that it looks a lot like something we already know how to do. And what is that? It's not exactly something we saw, but it's very, very similar to something we saw.
In least squares?
Yeah, it's basically least squares, right? I mean, if what is this? I mean, this is the same thing as like column by column. Let's do this. So let's say U prime xi, where xi is the ith column minus ai, L2 norm squared. So it's basically like the sum of a bunch of regression problems, right? Where I'm summing over the columns of X or the columns of A. So instead what you can do is do a sketch and solve or something, right? And don't get the X that actually optimizes this, but get an X which approximately optimizes this. And do that faster using sketch and solve. And then, that will give you, instead of X star, you'll get some X tilde star, and then you return the best rank K approximation of that. Okay, so.
Do we do that for like each of the I problems?
No, you don't even have to do that. that that will only come, the fact that it looks like regression, you just have to do in the analysis. But I mean, so if you want to actually just solve this, the way you do it is, so okay, so what you're going to do is sketch and solve. So maybe I should say this. So let's say generalized regression. So now you have something that looks like x beta, where beta now is, let me call it B for matrix, a matrix now. You want to minimize the Frobenius norm of xb minus y Frobenius norm squared. So you can imagine that each column of B is some beta, and each column of capital Y is some lowercase y, which is a vector that we saw before. So this is like basically the sum over all I of x. Well, actually, let me just say this. So yeah, so basically the way to minimize this is to choose B so that xb is the projection of y, like column by column, project each, you want to project each column of y onto the column space of x. So let's say you want to minimize this, right? So what, kind of the best thing you could do is make it so that every column of y is orthogonal to the column space of x, which you could just do using the same basic solution that you saw for least squares. So kind of beta star will be something like xx pseudo inverse x transpose y, I want to say. So like sketch and solve will give you something like beta tilde is something like pi x. This would be x transpose x. Pi x transpose pi x pseudo inverse pi x transpose pi y, where now y is a matrix. I mean, it's basically the same thing as regression. Does that make sense? You don't have to solve it. You don't have to solve it like one column at a time. You just do this, and that gives you the solution to the whole matrix problem. Okay. Okay, good. So I think now what I just want to show is like the claim that this is actually even a good thing to do. Right. The claim that this is good. So claim, if you define AK tilde to be the projection onto the column space of A pi transpose best rank K approximation in that column space of A, it satisfies A minus AK tilde for Frobenius norm squared is at most 1 plus epsilon, the actual opt, which is if you actually took the best rank approximation, as long as, now you need to say something about pi, right? So what's the thing that we're going to say about pi? As long as 1, we need that pi, oops. Pi is a 1/2 subspace embedding for some particular k-dimensional subspace, and we'll see what that subspace is. It'll come out of the proof. And 2, pi gives approximate matrix multiplication guarantees with respect to Frobenius norm with error, something like O of square root epsilon over k. And maybe here I should put an epsilon to be safe. Okay. So as long as pi gives, let's imagine pi is being chosen from some oblivious distribution. As long as for any k-dimensional subspace, it's a 1/2 subspace embedding with good probability, and for any particular matrices you're trying to multiply with good probability, it gives you error root epsilon over root k, then the claim is that this A tilde k is an almost optimal under Frobenius norm solution to low rank approximation. So we're going to prove this claim, but before we prove the claim, I just want to understand like what does this mean in terms of the dimensions of pi? So let's say that we have, count sketch. So 1 means that the number of rows has to be at least something like d squared. And 2 means that the number of rows has to be at least, not d squared, k squared. It has to be at least something like k over epsilon. Basically, it's like 1 over epsilon squared, where epsilon is your error, but our error is root epsilon over k, so it's k over epsilon. So this altogether implies that m has to be at least something like k squared. As long as m is at least something like k squared plus k over epsilon, that's good enough. Or another thing you could do is, like, let's say that is just a random plus minus 1 matrix. Then 1 means you just need m to be at least k, O of k, and 2 means that you need it to be at least, again, k over epsilon. So that implies that you can get away with m being something like k over epsilon. And we didn't talk about it in class. I mean, one way to go about it is to use a net argument together with fastjl. Another way is to directly analyze fastjl in the context of subspace embeddings. But you could do it with fastjl too. Basically pi being something like sampling matrix times Hadamard or Fourier times a diagonal matrix with signs. Then basically you can get away with m being something like, it's going to be something like k polylog k or something, k log k over epsilon, I think. Okay. So this is what it gives you in terms of like kind of what sketch dimension you can get away with to solve this problem. And again, remember now this m matters because when I was talking about runtimes, remember our runtimes here had some dependence on m, but m is basically going to be some k over epsilon or k squared or something like that. Okay, so what I want to do in the remaining time, and then I'll maybe have a little bit of time to say a little bit about what's coming next week on Monday, is just prove the claim. Prove the claim that this claim on this slide, as long as pi satisfies these two things, then finding the best rank k approximation in the column space of A pi transpose is a good thing to do. Any questions about this? No? Okay. Let me just put chat in case something comes up. Okay, good. So let's try and prove the claim. Okay. So let's prove the claim. So we want to look at, so let me actually say the following. Define P to be the orthogonal projection onto the column space of A pi transpose. So what we're trying to understand is, right, we said A minus AK tilde so let me actually do the following. So I'm going to define P to be the orthogonal projection onto the column space of the following matrix, which is the projection onto the columns of this thing, basically. So what we're looking at is this. Which I can write as AK minus PAK for Venus norm squared plus a K bar, I'll call it, minus PAK bar for Venus norm squared. When I say AK bar, what I mean is AK bar is just defined to be A minus AK. Right, so maybe you're not used to seeing this, but a fun fact is that the Frobenius norm squared of a matrix M, let me write that up top in red. The Frobenius norm squared of M is just the same thing as the trace of M transpose M. Okay, so I can write A is equal to AK plus AK bar, right? I can do that. And then if I look at the Frobenius, and then I can expand this out here as basically AK minus PAK plus, let me write it like this. Identity minus PAK plus identity minus PAK bar. And then that's the Frobenius norm squared of that. And then by this identity up top, Frobenius norm squared is just the trace of M transpose M. This is the trace of this whole thing transpose times itself. And the point is, if you look at, you're going to have terms that look like AK bar transpose AK, the cross terms. And those cross terms are zero, right? Because AK and AK bar have orthogonal columns, right? Because again, remember, what is AK? You take the SVD of A, and then AK is you keep only, let me maybe move here, right here. The SVD is equivalent to this thing, and AK means you only keep the first K, and AK bar means you keep the remaining things. AK bar is the remaining things, and those two matrices have orthogonal column spaces, right? Because again, in the SVD, U and V have orthogonal columns. So basically, if you take the trace, let's call this like W plus Z. If you take the trace of W plus Z transpose W plus Z, trace is a linear operator. So this is like the trace of W transpose W plus the trace of Z transpose Z. But then you have the cross terms plus the trace of W transpose Z plus the trace of Z transpose W. And the point is that these things are zero because the columns of W are orthogonal to the columns of Z. Okay, does that make sense? That's why when I expanded, that's why I can write the Frobenius norm squared. I can decompose it as these two sums that don't interact with each other. Okay. And then now, what is this? This is equal to identity minus P AK bar Frobenius norm squared, which is at most, again, we had this identity before. Another identity that I'll write above is that if you look at the Frobenius norm of WZ, it's at most the operator norm of W times the Frobenius norm of Z. What's the operator norm of identity minus P? Well, identity minus P is a projection matrix. It's a projection onto the orthogonal space to P. So any projection matrix has operator norm at most one. You can't, orthogonal projection can only decrease norms, not increase norms. So this has Frobenius norm squared at most AK bar Frobenius squared, which is just opt. Okay. So the name of the game really is bounding this thing. We want this to be at most like some, O epsilon times opt. Okay. Okay, so let's bound this thing. And as we're going to see, it turns out that this thing is very closely related to regression. Okay, so we have that AK minus PAK for being storm squared. Well, just expanding out what that projection thing is, that's equal to AK minus A pi transpose pseudo A pi transpose pseudo inverse times AK for being storm squared. Right? We project it onto the column space of A pi transpose. And then let me take transposes on both sides. I mean transpose of the whole thing. This is equal to AK transpose. Actually, let me write it let me also do it this way. Yeah. So let me take transpose. This AK transpose minus AK transpose. And then I'll write here pi A transpose pseudo inverse pi A transpose. And let me just take the negative on the inside. That doesn't change the Frobenius form. That's equal to AK transpose pi A transpose pseudo inverse pi A transpose Frobenius form squared. Okay. And again, if I sum up over columns, I'm missing a minus sign. Oh, minus AK transpose. So let me sum up over columns. This is sum over all I of AK transpose pi A transpose pseudo inverse pi A transpose ith column minus AK transpose ith column L2 norm squared. Okay, so I know this looks a little bit like a mouthful, but let me rewrite the last thing on the next whiteboard. So what I said is that AK minus PAK Frobenius norm squared is at most the sum over I of AK transpose ith column minus, actually, no, that's not what I want to say. AK transpose, and then I've had something like pi A transpose pseudo inverse pi A transpose ith column minus AK transpose ith column L2 norm squared. Okay, so I claim that this looks very similar to, it's not exactly the same as, but I claim that it's very similar to, again, something that we've already seen. Does it ring any bells for anyone? Imagine for a second, this is not what we have, but imagine for a second that this was actually, A transpose I. Now, does it look like anything? Okay. Maybe it just looks like too much of a mouthful that everyone got scared. Or maybe people are actually with their videos off working on their project proposals. But basically what I wanted to say was, if it had been A transpose I, this is exactly the error from sketch and solve regression, right? Imagine a regression problem that looked like as follows. Imagine min over x of something like AK transpose X minus A transpose I, L2 norm squared. Right? This is a regression problem, right? A transpose I is a vector. AK transpose is a matrix. Find the vector X which minimizes the L2 norm squared. Using sketch and solve, we would find some X tilde, which is the minimizer of the pi version, pi AK transpose X minus pi A transpose I, which, there's a closed form solution for what the minimizer is. It's basically you want X to be such that pi AK transpose X is equal to the orthogonal projection of pi A transpose I onto the column space of pi AK transpose. Okay, so I know that sounded very annoying to say, but this is just exactly equal to pi I guess this should have been a pi AK transpose. Pi AK transpose pseudo inverse pi A transpose I. Okay. So I guess I should have said that it's not exactly the same. It's the same if that thing had been A transpose I as well as this thing had also been an AK here. Then it would have been exactly the same as a regression problem. Okay. Yeah, so it's not exactly the same, but now what we can do is we can basically try to use our analysis from last time, I guess our lecture on Monday, which did the following thing. Let me go to Monday's lecture. Okay. So just, I know this is there's a lot of this is pretty calculation heavy, but all I want to say is you can basically use some of the tools from Charloche's AMM style analysis of sketch and solve and plug them into our current situation. So in particular, if you look at the definition of gamma here, so what was okay, so let me copy over some of this stuff to our situation. Oh, did I accidentally throw something away? So Charlotte's idea is to analyze sketch and solve. He made a few definitions. One is that now it's a matrix, but say W is the residual matrix from choosing the optimal solution to regression. And then also, there was also this thing where you defined U alpha, or gamma, I think, was defined to be A times X tilde star, which is the sketch and solve solution minus X star. And if you remember, we said something like last time, we said something like gamma. Well, here now gamma is going to be a matrix. So let's say that was a vector. We said last time gamma L2 norm squared was at most, and there's like a 1/2 here or something, was at most pi u transpose pi u gamma L2 norm squared, which we said was equal to pi u transpose pi w L2 norm squared, which we argued was at most some like epsilon prime times the Frobenius norm of u times the norm of w, which is just root opt. If it's a squared, I guess this is all squared. So this was opt, and this was d. Okay. So we'd like to do that kind of thing here where we can now basically relate this to things that look like the norm squared of some gamma i's, and then basically we want to sum up the square norms of the gamma i's. We're going to do exactly the same, this chain of inequalities, and get something on the right hand side where instead of the matrix U, it's going to be some matrix which depends on which is not U, but something like UK or maybe VK. And it's going to have Frobenius norm squared K. And then we're going to be able to leverage approximate matrix multiplication with error parameter root epsilon over K instead of root epsilon over D. Okay. So, yeah. Actually, let me just, I just give myself a second. I think I confused myself on one calculation. Okay, I'm going to fix this in the notes, but I think I should have ended with this thing here, actually K, but let me go with that being K, and then I'll fix it in the notes. So what I was saying, okay, so good. So now what we have is I said something like we have the sum over I of that term, which is AK transpose pi AK transpose pseudo inverse pi A transpose I minus AK transpose I. Okay, and I'm comparing this to the regression problem I said, min over x of AK transpose x minus A transpose I. Okay. So if I looked at the term, look at AK transpose x tilde minus x star, where this is the true opt, and this is the solution to sketch and solve. Okay. So what is AK, what is the true optimal solution to this problem? The true optimal solution is basically you want to make, okay, so pretend that, so you want to project A transpose onto the column space of AK transpose with as little error as possible. And another, so if you get rid of the transposes, you want to project A onto the row space of AK as best as possible. And the best way to do that is just to simply choose AK. Okay, so your projection, you're going to pretty soon project onto VK. So the true optimal solution has AK transpose X star equal to AK transpose I. Right, so project onto basically VK. Okay, where V is the row space. The columns of V form a basis for the row space of A. So, and then we already know what this is. The solution to sketch and solve is exactly what we had above. This is going to be pi AK transpose pseudo inverse pi A transpose I, which is exactly the same as this. Okay. So this is exactly equal to the sum over I of kind of, I'll call it AK transpose X tilde I minus X star I. L2 norm squared. And then by definition of gamma, right? Gamma from our previous analysis of sketch and solve using AMM is exactly this difference of A times the optimal, A times the sketch and solve solution versus the optimal solution. So this is equal to the sum over I of basically U times gamma I L2 norm squared, which is equal to the sum over I of gamma I L2 norm squared. Okay. And then the solution, the analysis is exactly the same as last time. Sum over I gamma I L2 norm squared is at most. So now we use the fact that we have a subspace embedding for the row space of VK, or for the column space of VK. So this is at most, let's say 1/2 times pi VK transpose pi VK gamma I L2 norm squared, the sum over I, which is the same thing as treating gamma as a matrix now, pi VK transpose pi VK gamma for being a norm squared. Right, and then now what we say is that this thing is equal to pi VK transpose pi, and then we replace this, not this, we replace we basically say that VK, sorry. Pi W and pi beta, so this is pi beta, pi, good, so we put a W here. Right. So the claim is that this thing and this thing have the same projection onto the column space of pi VK transpose. And that's exactly what we saw before with AMM, the AMM analysis with Charlotte, which I'll go to right now. This, right? So that's exactly the analog of this, which said that this thing and this thing have the same projection onto the column space of pi u. Okay. And then you use approximate matrix multiplication to argue that, well, this is just now, this is equal to, I'll write it as pi vk transpose pi w minus vk transpose w. This is 0. But by AMM, this is at most epsilon prime squared, or epsilon prime is your error, times the Frobenius norm squared of vk times the Frobenius norm squared of w. This is opt. This is k. So if I set epsilon prime to be something like root epsilon over k, this implies that this is at most epsilon times opt. Okay. So I apologize. That was a bit of a mess, and I feel like I didn't deliver that as clearly as possible. But I'll put it in the notes so you can review it. And also I'll say that kind of maybe the punchline to take away from all of this is you expand out what your error is. You look at the terms that you show up, and you realize the terms that show up are basically identical to terms that showed up in the analysis of Charloche's sketch and solve error for least squares regression when you depend on subspace embedding for a certain subspace as well as approximate matrix multiplication. So the only thing that changes here is like, what is the subspace? The subspace is VK. It's the column space of VK. And that's basically it. So I guess, are there any questions? Are there any, I realize that took longer than I expected to, so we're out of time. But are there any questions about this? Okay, so everyone's gone. So I guess I will see you all. I will see you all on Monday.
All right.